stand in front of any materials laboratory today, carbon nanotubes being assembled atom by atom, graphene sheets engineered for impossible strength, metamaterials that bend light itself, and you're witnessing the cutting edge of human innovation. But what if I told you that some of the most revolutionary breakthroughs in advanced materials aren't waiting in the future, but buried in the past? What if a Viking blacksmith working by firelight in a frozen northern workshop over 1,000 years ago accidentally discovered principles that could transform everything from aerospace engineering to medical implants? This isn't romantic nostalgia. This is hard science colliding with ancient craft in ways that are forcing us to completely rethink what we know about materials engineering. Picture a Viking sword pulled from a Norwegian burial mound, corroded, ancient, seemingly unremarkable. But place it under an electron microscope, and something extraordinary emerges. The blade's microstructure reveals patterns that shouldn't exist. Microscopic layers of varying carbon content, grain boundaries organized with almost mathematical precision, and trace elements distributed in ways modern metallurgists struggle to replicate intentionally. These weren't crude weapons hammered out by barbarians. They were sophisticated composite materials engineered through processes we're only beginning to understand. The Vikings called their best blades Ulfberht, swords so superior they seemed magical to their enemies. They could cut through inferior weapons like scissors through cloth, yet remain flexible enough to bend without breaking. For centuries, historians assumed this was exaggeration, legend inflating reality. Then modern analysis revealed the truth. Ulfberht swords contained carbon steel with purity levels that shouldn't have been achievable until the Industrial Revolution, nearly 800 years later. The Vikings were working with metallurgical sophistication that vanished from Europe and wasn't recovered until blast furnaces and precise temperature control became standard. That's where this story gets fascinating. The answer begins in bogs. The Vikings extracted their iron from bog iron ore deposits formed in wetlands through bacterial action. Modern metallurgists initially dismissed this as primitive, inferior material. But recent analysis reveals something unexpected. Bog iron contains trace elements, vanadium, molybdenum, manganese, in unique combinations. When processed correctly, these so-called impurities don't weaken the metal. They enhance it, creating microalloys with properties that pure iron could never achieve. Here's the revolution hiding in plain sight. We've spent the last century pursuing purity in materials, the purest silicon for computer chips, the purest titanium for aircraft, the purest everything. But the Vikings worked with a different philosophy, controlled complexity. They didn't fight impurities, they harnessed them. They created materials that were heterogeneous at the microscopic level, with each layer and inclusion serving a purpose. Now, let's take a look at what's happening in advanced materials labs today. Researchers are discovering that actually the strongest and most versatile materials aren't pure. They're these carefully engineered mixtures. High-entropy alloys, for instance, combine 5 or more elements in nearly equal proportions, creating properties that are just impossible in pure metals or simple alloys. Nanocomposites, on the other hand, layer different materials at scales the Vikings couldn't have seen, but somehow they kind of intuited. So, in a way, we're rediscovering, with billion-dollar equipment and AI-assisted design, the same principles that ancient blacksmiths understood through experience and inherited knowledge. Consider pattern welding. The Viking technique of forge-welding multiple strips of metal together, folding and hammering them again and again to create hundreds or even thousands of layers. For decades, modern metallurgy dismissed this as purely decorative, just making those beautiful swirling patterns on blade surfaces. But then, engineers working on laminated composites for aerospace applications noticed something interesting. The performance characteristics of pattern-welded steel, its ability to resist crack propagation, its combination of hardness and flexibility, actually mirrored what they were trying to achieve with modern composite materials. The Vikings were creating functional gradients in their materials a whole millennium before we even had the mathematics to describe why it worked. Each layer had slightly different properties. Cracks starting in one layer would hit an interface and either stop or deflect, rather than propagating catastrophically through the entire structure. This really is biomimicry, the same principle that makes bone incredibly tough, even though it's made from relatively weak materials. Bone achieves its strength through hierarchical structure, right from the molecular level up. Viking swords, in their own way, did the exact same thing. Now, imagine applying these principles at the nanoscale. Researchers are using additive manufacturing, basically three-dimensional printing for metals, to create materials with deliberately varied composition and structure throughout a single piece. Think of a turbine blade that's hard and heat-resistant at the edge where it faces combustion, but tough and flexible at the root where it attaches, or, say, a medical implant that's rigid where it needs to bear load, but gradually becomes more flexible to match the surrounding bone, reducing those stress concentrations that, often cause failures. These aren't just improvements, they're paradigm shifts, and they're all based on abandoning the pure is better mindset and embracing the kind of controlled complexity that Vikings really mastered. Then there's the question of process. Vikings achieved temperatures high enough to work steel using charcoal, bellows, and intimate knowledge of fire behavior. No precise pyrometers, no computer-controlled atmospheres. Yet they consistently produced results. How? Well, recent experimental archaeology suggests they relied on color, sound, smell, and even taste, sensing the chemistry happening in their forges through every available sense. They developed what modern researchers would call embodied knowledge, understanding their materials at a level that honestly went beyond conscious analysis. Today, as we push towards sustainable manufacturing, this matters enormously. Modern metallurgy is, incredibly energy-intensive, requiring massive infrastructure and enormous heat. But what if we could achieve similar or even better results through lower energy processes, informed by ancient techniques? Researchers are exploring exactly this, using AI to analyze historical metal artifacts, identifying the chemical signatures of ancient processes, then designing modern equivalents that achieve the same microstructural results with less environmental impact. Machine learning algorithms are now being trained on databases of ancient metal compositions and structures. The AI doesn't know it's looking at Viking swords, it just sees successful materials with desirable properties, and it works backward to understand what conditions produce them. Some of the alloy combinations and processing pathways it suggests look, honestly, remarkably similar to what Vikings actually did. The difference is now we understand why it works, and can intentionally reproduce and refine these approaches. This convergence of ancient craft and cutting-edge technology reveals something, well, truly profound about innovation itself. We often assume progress is linear, that each generation necessarily knows more and does better than the last. But knowledge isn't always cumulative. Techniques get lost, understanding fragments, and sometimes wisdom from the past contains insights we're only ready to appreciate with modern tools and perspectives. So the future of materials science might not be about, abandoning historical methods, but about really understanding them deeply enough to apply their principles in new contexts. Viking blacksmiths, for example, couldn't explain grain boundary engineering or work hardening in our modern terms, but they definitely understood these phenomena intuitively and used them masterfully. Now we have the analytical tools to actually decode what they knew, and with today's technology we can apply those principles at scales and in materials they never could have imagined. So, could Viking metallurgy forge modern supermaterials? Well, the answer is already yes. It's happening right now, in labs where materials scientists are consulting with archaeologists, where AI trained on ancient artifacts is suggesting novel alloys, and where, honestly, the philosophy of controlled complexity is starting to replace the pursuit of sterile purity. The Vikings didn't have our tools, but they had something equally valuable. Generations of accumulated wisdom about working with materials in ways that embraced, rather than fought, natural complexity. They created marvels without understanding the science. Now we have the science. Combining both might give us materials that just years ago seemed impossible. This story matters because it changes how we think about progress and innovation. The next breakthrough might not come from the newest laboratory or the most advanced equipment. It might come from a researcher willing to look backward as well as forward, to find wisdom in unexpected places, to recognize that ancient doesn't mean primitive. Subscribe to Through Time, because the future isn't just ahead of us. Sometimes it's buried in the past, waiting for us to be smart enough to recognize it. Share this story with anyone fascinated by the intersection of history and innovation, because honestly, understanding where we've been might be the key to imagining where we're going. The Vikings are still teaching us. We just needed to learn how to listen.